Here at the Neuromuscular Rehabilitation Engineering Laboratory at the University of Rhode Island, our team of biomedical engineering researchers work on a broad range of prosthetic design and control technologies, all geared towards creating the next generation of powered prosthetic devices and continuing to enhance the quality of life of our nation's growing amputee population. The lab's efforts center on three main areas of ongoing research. The first is the design and implementation of a comprehensive prosthetic control system called a neural-machine interface, which identifies user intent by decoding the muscle activity from an amputee's residual limb. A second focus on characterizing the modified stumble responses of amputees has led to the development of advanced dynamic stumble recovery and fall avoidance safety mechanisms. A third focus centers on the design and development of new powered prosthetic devices, which incorporate these advanced control systems into compact, self-contained prostheses. The following video clips demonstrate recent advances in each of these three areas. Evaluating a real-time neural-machine interface using virtual reality. This video demonstrates the preliminary real-time testing of a novel neural-machine interface, or NMI, on a single transfemoral amputee. The test subject is asked to perform level ground walking, stair ascent, and stair descent tasks. The NMI senses both neuromuscular signals from the human body and mechanical measurements from the prosthesis to drive a virtual reality representation of the subject in order to safely evaluate the NMI's ability to accurately predict the user's intent. In this example, an avatar was displayed on a TV monitor in order to visualize the NMI's predictions in real time. The system demonstrated high accuracy and reasonable latency, promising results that led to the system's further refinement. Real-time implementation of the neural-machine interface on an embedded system. Real-time implementation of our developed neural-machine interface on a high-performance embedded system is demonstrated in this next experimental trial. The embedded system consists of two major parts: a microcontroller unit for sensing the neuromuscular signals from the human body and mechanical measurements from the prosthesis, and an FPGA device as the computing engine for fast signal decoding and pattern recognition. The designed NMI prototype was tested on an able-bodied subject to accurately classify multiple movement tasks in real time. These results demonstrate the feasibility of a self-contained and high-performance real-time NMI governing the control of artificial legs. Stumble detection in prosthetic limbs. Recent design advances have led to a new potential for powered prostheses to allow amputees to actively recover from stumbles and avoid falls. To achieve this goal, promptly and accurately identifying stumbles is essential. In this video, the normal gait of a transfemoral amputee was perturbed by a variable speed treadmill. Several data sources, including the acceleration of the prosthesis and multi-channel electromyographic signals recorded from the residual thigh muscles, were monitored. This study had two goals: select potential stumble detection data sources that react reliably and quickly to stumbles which can be measured from the prosthesis, and to investigate novel approaches to detect and classify differing stumble types in patients with transfemoral amputations during ambulation. The data gathered during this research lies at the foundation of more comprehensive automated safety mechanisms. Real-time performance of a truss sensor interface. The development of a reliable and trustworthy NMI is a critical step in the safe and intuitive control of prosthetic legs. To achieve this goal, a truss sensor interface was designed to monitor the diverse disturbances generated by the environment, which may distort EMG signals, cause errors in the NMI, and ultimately threaten the safety of prosthetic users. This video demonstrates the preliminary implementation of a designed truss sensor algorithm, conducted on an able-bodied human subject asked to perform sitting and standing task changes. While the subject performed the tasks, disturbances were introduced into the NMI sensor system. The results demonstrate fast and accurate detection of disturbances, allowing for greatly enhanced neural-machine interface reliability. Preliminary testing of a prototypical powered prosthetic knee on a transfemoral amputee subject. In addition to the development of a robust NMI, The design and testing of advanced powered transfemoral prostheses is a major research focus. This video documents preliminary testing of a recently designed powered prosthesis on a transfemoral amputee patient. The subject was instructed to walk on a treadmill on level ground and to ascend and descend a ramp. Walking patterns were further improved through the instruction of a physical therapist present during trials, allowing engineering improvements to better reflect current best practice rehabilitation strategies. Preliminary evaluation of a neural machine interface on a prototypical powered prosthetic knee. In this video, neural control of a powered transfemoral prosthesis was developed and evaluated on a unilateral amputee subject. The prosthesis control system consists of a high-level neural controller based on our previously developed neural machine interface and a low-level intrinsic controller. Neuromuscular signals recorded from residual thigh muscles, ground reaction forces collected from the prosthetic pylon, and triaxial accelerometer readings measured from the residual thigh segment were used as the NMI inputs to recognize user intent. The subject was instructed to continuously perform several tasks, including standing, level ground walking, and ramp ascent and descent. The resulting data showed that the neural controller accurately and responsively adjusted the prosthesis control pattern based on the user intent, and allowed the user to safely and smoothly transition between tasks. These results demonstrate the potential of our designed NMI to govern intuitive neural control of increasingly advanced powered lower limb prostheses.